Welcome to day 2 on partial fractions. Now, to do these are the same. The only difference is what you're going to notice is that we are going to have a nonlinear factor in the bottom. And in order to do this one, we have to do it just a tad bit different. We're still going to do the same. We still have 2 factors in the bottom. So that means we're still going to have 2 fractions we have to add. We're still going to have an x and this x squared plus 10. Now, I'm just going to kind of sum up these ones and actually show you an easier way to do this one. But if you want to, you can follow along here. But basically, to do this, the same thing. I have to do one less power than on top here. And that's kind of what this is saying right here. Whatever the factor is, you got to do one less power. So if the power is 1, I have something with 0 power, so a. But if the power is 2, that means I have to have a linear factor on top, something linear on top. And so that becomes bx plus c. And we're going to do bx plus c. We just want the power to be 1 less than the bottom. So the bottom is 2, the power is 1. And we solve it the same exact way. We multiply through by our LCD, x and x squared plus 10. And doing that, hopefully we kind of caught on. This just goes away. 2x minus 3 equals a. The a is missing the x squared plus 10. And then we get this bx plus c times x. Now this is going to cause us trouble later on, but I'm going to show you a neat way to get rid of this one that we're going to use quite a bit in calculus, okay? A little bit different than the directions here, but I promise you it will be easier. Alright, we solve for our 1, 0 that we have, and that would be x equals 0. This one can't give us a 0 because of imaginaries. If I plug in the 0, we're going to get negative 3 equals 10a plus on all of this basically becomes 0. So our only known one we get a is negative 3 over 10. Now, to get b and c, we are going to use an old algebra trick, okay? We're just going to rewrite this. 2x minus 3. We only do this if this power is different than 1. 2x minus 3 equals, we just had a is negative 3 over 10, and we get x squared plus 10 plus bx plus c x. And it's really cool what we're about to do here. If I distribute, I get 2x minus 3 equals negative 3/10 x squared minus 3 plus bx plus c times x. I'm not going to distribute here for a second. Now what happens is if I combine my like terms, these negative 3's will cancel. And if I bring this over, I get negative 3/10 x squared plus 2x equals, now watch what happens if I distribute, bx squared plus cx. Do you see it? Do you see it? These are equal. Because these are equal, the like parts must also be equal. Which means, what's b going to equal? Well, b is my x squared term. What's my x squared term here? Negative 3/10. C is my single term. So what's my single term over here? 2. So c is 2. And we already got a earlier as negative 3 over 10. So now when I write my expansion, remember it was a over x plus bx plus c over x squared plus 10, and that's going to give us negative 3 over 10x, really cool way to write that one, plus now b, we don't normally like to write like this, but we're okay, negative 3 over 10x plus 2 for my c over x squared plus 10. Now this is okay to write, but we don't like that 3 over 10, so at the end we just multiply both top and bottom by 10, and that's going to clean it up for a little bit. And we get negative 3 over 10x plus, distribute here, a negative 10x, whoops, ooh, that's embarrassing, a negative 3x plus 20 over 10 times x squared plus 10. And it's okay to leave it like that, okay? And there's our answer. A little bit harder. Definitely try this one. Maybe again. Okay. Now we also talked about we can do it away with using systems, and we can talk about an example like that tomorrow. Okay. All right. So let's take a look at example number 2. Same type of problem. I've already have it expanded for us. So this becomes a. This is my linear term. x minus 3 plus b, and this of course becomes x squared plus 5. Whoops. Because of the square, though, we should go bx plus c. There we go. Sorry about that. Multiply by your LCD. That's going to be x minus 3, x squared plus 5. So we get 8x squared minus 18x plus 10 equals a x squared plus 5 plus bx plus c times x minus 3. My 1, 0 is the 3 from over here. So if I plug in 3, we get, what's that, 6, oh man, 9 times 8, 72 minus, what is 18 times 3, what's that, 54 plus 10 equals, oh my gosh, 14a plus, and all that just becomes 0, thank goodness. And let's take a look here. What is 72 minus 54? I'm going to use a calculator here to help out. 72 minus 54 plus 10, we get 28. Oh, that's not too bad. 28 equals 14a, a equals 2. And now remember, to get b and c, we're just going to rewrite this out. 8x squared minus 18x plus 10, a is 2, 2x squared plus 5 plus this bx plus c times x minus 3. And now what I'm going to do is I'm just going to distribute. 8x squared minus 18x plus 10 equals 2x squared plus 10. And I'm going to leave this alone for right now. bx plus c, x minus 3. See what might happen here. Bring these over. We're going to get 6x squared minus 18x. The 10's cancel, equals bx plus c, x minus 3. And now watch what happens. I could factor out a 6 and an x. And if I factor out the 6x, that's going to give me x minus 3. Now, why is this important for us? What factor do both sides have? An x minus 3. We can actually cancel those out. So we get 6x equals bx plus c. And match up your like parts. What's b going to equal? It has the x, so b is 6. Now c, there's nothing to match up with c, so what could that be? 0. So when we write out our equation now, I'm going to go way up here. Okay, a we found was 2, b is 6, c is 0. So I could write this then as 2 over x minus 3 plus 6x over x squared plus 5. And there is our polynomial. Okay, now let's start number 2. This one is not very pretty to do. Mainly because, take a look, it's squared and they're nonlinear factors. Okay, so we're going to go ahead and start this one here. And up top here, be careful, they both have to have an x squared plus 3. Remember, from yesterday, each factor, each power gets its own denominator. So we get x squared plus 3 and x squared plus 3 squared. We're going to write this one as ax plus b because it's quadratic, and this one too, but we got to use different variables, cx plus d. Now, when you do your LCD, same way, when we do our LCD, what we're going to wind up with is x squared plus 3 squared. And I take a look at what each one's missing. This has both x, 6x cubed plus 16x equals. Now, the ax plus b, it's missing another x squared plus 3. But the cx plus d, it has everything with it. Okay, that's a D, not a parenthesis. Alright, so what we're going to do is we're going to take a break right now, see if you can finish this up, try to work numbers 1 in the first example again, and we'll come back after break and we'll take a look at finishing this one up, okay?